Then we'll move on to sort of like maybe atomic theory. And then after we move on to that, then we'll go to decay. So we'll learn some weird stuff, and we'll learn a little history about the theory of the atomic model, and then some new stuff as well, and then we'll learn about what happens when things break down, right? That's the general idea. So let's see if we can do this quickly. First of all, relativity. What is the speed of light anywhere in the universe all the time? 3 times 10 to the 8th meters per second. That is the speed of light always, anywhere, all the time. Does this make sense to you? Yes. Okay. If that's true, and that makes sense to you, then let me pose to you this problem. If Thomas is standing on the side of the road, and I'm driving by in my car at like 40 miles an hour, and then I see him, and I don't know, whatever, like, I bought some watermelons. And when I'm like, hey, you want a watermelon? He's like, yeah. So then I just toss the watermelon out the window.
That's going to hurt.
How fast is the watermelon going to hit him?
Either a little over or a little under
40 miles an hour, right? Or we can do this. Let's say Thomas and I did this. I bet one of my physics classes, I said, I bet that I can throw a baseball 400 miles an hour. I can throw a baseball to a speed so that it reaches a speed of 400 miles an hour. And like, no, you can't do it. And then how did I do it?
Got a car.
You threw in a car.
Car that goes 400 miles an hour?
But you on an airplane that was going.
Yeah, an airplane. Okay, airplane is when they're taking off as they're ascending, you pass through 400. They usually cruise around 500 miles an hour. So you can. So if I just am in the airplane and Denise, sorry, Michelle's in the. What do I call you, Denise? Do you know anyone named Denise?
My mom.
Oh, really? Okay, well, anyways, Michelle's in, and if I just toss Michelle the ball like this, just nice and easy, you see the ball has a velocity at 400. So if I toss it at 1 mile an hour, what is the new velocity?
See that target.
You just said there's no target.
Oh.
We're not in school. Yeah.
Okay, so not trying to say I don't want to be here, but like someone said this is only for people taking the
Nope,
class.
it's everybody.
Okay.
Because this is going to be on your final, too.
Oh, okay.
Okay, so, I'm not saying I want to be here, but I don't have to be here. I want to be here. So, does it make sense to you that by throwing the ball 1 mile an hour, I've actually thrown the ball to a velocity of 400 miles an hour? Just depends on what your relativistic frame is, right? It depends on what you're relating the speed of the ball to. So compared to the ground, it's 401. Compared to the people on the plane, it's 1. Everybody cool with this? No? Okay, so if we're in a car going 50 miles an hour, and I toss you, I don't know, whatever, like something, but you're in the car with me, so I toss it to you. How fast does that thing move? Yeah, okay, so you get it, right? That's the idea, that when you're in some moving frame of reference to another frame of reference, you have extra velocity, right? Okay. What did we say the maximum speed of light is? 3 times 10 to the 8. What happens if I'm in the car, or in the plane, or as your book uses the example, in a train, and I turn on a flashlight?
Just a little bit.
Do you see what I'm saying? There's a problem. Because if I'm moving at 100 miles an hour, and I turn on the flashlight, does that mean the flashlight, or if I'm moving at, let's say, 100 meters a second, does that mean the light from the flashlight is now moving 3 times 10 to the 8 plus 100?
No.
It's not 300 million and 100 meters per second. It's still only 300 million meters per second. Okay, how is that possible? True, but do you see the problem? When you have velocities, an object in motion, and then you add a velocity to it, that velocity is cumulative with reference to the ground. So how come when I'm in the car going 50, I'm in the plane going 400, and I turn on a flashlight, the photon that comes out of the flashlight is only moving at 3 times 10 to the 8th. It is not moving at 3 times 10 to the 8th plus 100.
What's weird?
It's because of a concept called time dilation. Right? Because, like, that thing moved farther in that distance. It had a greater velocity. So what has to happen is this. C is constant, no matter what. That's x over t, right? And in general, this is 300 million meters per second. Okay? So what happens is if I have some system where I'm shooting light in an object that's moving fast, a train, a plane, an automobile, whatever, then this is going to get, like, the distance that it covers will get, like, is longer because it's added velocity. So what happens to time is time gets fatter. The seconds get fatter. They expand. They dilate. Do you know what it means when your pupils dilated? Boop, they expand. So time dilation means that light, even if you go faster, right? If you move your flashlight at 10,000 meters per second, the photons that come out of the flashlight have to stay moving at that speed. And since you're moving the photons on top of the speed of light, they're going to cover a farther distance. Yes. And in order for that to stay constant, this bottom, I mean, does that make sense? If the top gets bigger, but this stays the same, what has to happen to the bottom? It has to get bigger. Does this make sense to you? Well, it's pretty good, because it doesn't make sense to most people. Okay. What's that?
It doesn't make sense.
Okay.
I'm sure the next thing you say will something.
What's that?
I'm sure the next thing you say will something.
One helps. Okay, maybe think of it like if for, I don't know if this analogy is going to work. It's probably going to screw it. But like if you can only take 100 steps, that's it. You have to step 100 times. You are not allowed to step any other or any fewer or any less. And I say go from here to the other side of the group. What's going to happen to the size of your steps? They're going to be small. Right? Does that make sense? Now, if I say go from here to the front office, now what's going to happen to your steps? See, the number of steps cannot change. But since the distance got bigger, the steps got bigger. So here, what's happening is since the speed of light cannot change, when you make the light go a farther distance, time itself has to stretch out so that it's the same number of seconds, or the seconds are the same fatness, expand to fill in the gap of this increased distance.
Okay.
It's kind of weird. But. And then it changes by a factor of that there's a relativistic relativistic denominator. It's like this. Right? This root, right? This thing here, that's the thing that you use to multiply things by so that you can see how much they adjust for relativity. And you can see that if the velocity is very small, what happens? If v is very small, what happens? It's like 0. So the square root of 1 is 1. So how fast do you have to go to make a significant bump here? Do you see? You have to go close to the speed of light. This brings in a concept called the twin paradox. Okay? If, let's say, we had two people who have the same birthday, I don't know who that is, Jamie and Helen, whatever. I don't think they do, but whatever. So their birthday is today, May 3rd. And then Helen, being the adventurous person she is going on a space travel trip to, like, Alpha Centauri or something. No, she'd never do that. Let's say to, like, Pluto or something, right? Because she wants to see this thing that got Pluto.
And she goes really, really fast.
Yeah, well, now that there are new advances in speed of spaceships, she can travel almost the speed of light. Okay, so whoop, she goes out to Pluto, whoop, she comes back, like, I don't know, a couple months later. What has happened on Earth?
Lots of times, yes.
Why?
Because time shrunk around you. Time stretched around you.
Yes, right? So let's say in that month, you would expect, I don't know how long, let's say you would expect Jenny to age 100 million, or whatever, like 100,000 seconds. That's not even a month, but whatever. You get what I'm saying. We expect her to age 100,000 seconds. In that space of her time, what happened to her seconds? Because she was traveling close to the speed of light. They expanded. So she actually lived fewer seconds. So that when she comes back to Earth, Jenny now has grandkids, and she's still Helen. No, not that Jenny wouldn't be Jenny, but
Wow.
So would that mean that if you were able to travel at the speed of light, time travel is possible?
only into the future. Basically, you leave, and you. So so remember, the closer you go to the speed of light, what happens to time?
Time expands.
It expands, which means it slows down.
What would Helen feel like?
She feels perfectly normal.
So it just feels like
It's kind of like, imagine
Based
two
on
clocks
her-
going tick, tock, tick, tock. When she speeds up towards the speed of light, it's like tick, tock, tick, tock, tick. See what's happening?
Those are really hard to do.
It's pretty hard to do. It's taking a lot of concentration. No one can see what I'm doing. So the two kind of pendula that are going, the one on Earth stays spinning or stays ticking at the same speed, but the closer she gets to the speed of light, this factor expands time. So each second is fatter. So her clock ticks less. And because it ticks less, she ages less. So she's only lived 20,000 or 15,000 seconds in the time that she's lived 100,000. And boom, right? So that's called the twin paradox. They're the same age when one leaves, as one comes back, one's an old man, one stays younger. Okay, all right. So there's also other things called length contraction. Because like if I'm standing on the side of the road, car goes by, right? That car passes me in a certain amount of time. But if that car is approaching the speed of light, then the time units that car passes me stretch out. So then that causes my perception of the length of the car to get, actually it causes the physical length of the car to shorten. Okay, don't worry about it. Okay, anyways. Just know that there is this concept called time dilation. I'm not going to go into length contraction too much because they don't really ever talk about it. But the other thing is length contraction, just so you know. And it's just the actual physical length of an object is affected by the speed at which it travels.
That is once you get bigger. It's like as you approach the speed of light, you get so massive you can no longer move.
Oh, yeah, there's that has to do with energy. We'll talk about that in a minute too, so that's good. All right, questions so far about that? That's pretty mind-bendingly weird stuff. And you can, like, the basic equation works out something like this. Oops, p squared over c squared. So it's something like that. Yeah. And you see, so as this gets very close to the speed of light, then this gets knocked down to some decimal. And then when you take the square root of a decimal, you get Yeah, you're guaranteed to get a decimal, right? So you get a really small decimal that shows you the percent, the amount of change. Okay, all right. So that's it for relativity. Oh yeah, take out your formula sheets, please.
Why does Happy think he's going to get recorded this?
What's that?
Why does Happy think you're not going to get supported?
Because you're traumatized, that's why.
Okay.
Okay, so as you can see from here, there's no relativistic equations in here. So I just threw that ratio, the root up there, so you can kind of know what it is I'm talking about. And then I wanted to do the length contraction thing so you could see how it would work. But that root is multiplied or something is divided by that root to show time is 1 over. So that's a fraction, right? So it's a decimal. And if you divide by a decimal, what happens to your number? Yeah, it gets bigger, right? So if you divide by half, it's like multiplied by 2. Okay, so that's the time dilation part. And then length contraction. The things that actually affect the problems that you're going to be dealing with are these questions here, which we'll begin to move in next. So yeah, I just wanted to calm your heart about there's not any relativistic calculations in here. Okay. Next comes, let's do this, what did I call this? Atomic structure or something like that? Theory, there you go, atomic theory. All right, so a long time ago, like atomic theory kind of works out, well, you've taken chemistry, how did that idea pop up? Atomic theory, where did the idea of the atom come from?
Oh,
The Greeks.
Yeah, the Greeks, right? So some guy named Democritus, I think it was. Can't remember if that's exactly his name, but whatever. It's a long time ago, who cares? You could say his name's Bob. But anyways, this Greek guy figured out that everything is sort of constituted of the same stuff. So he thought everything was exactly the same stuff, just like in little tiny BBs or something, right? And then that theory sort of evolved, right? Dalton, so we have Democritus, we have Dalton. Dalton was this British guy who came up with the plum pudding model. Oh, whoops, I have to put Thomson. All right, Thomson. Yeah, Thomson was a guy who, what did Thomson do?
Electric.
Yeah, he discovered, Thomson figured out that there are these things called electrons, they're negative charges. And he created a way using magnets and electricity, like to stream them off and make streams. No, that's actually Rutherford. Or, well, actually, well, whatever. I'll get to it in a second. Those kind of monitors back there, if you ever see these old-fashioned, big, fat, giant glass monitors, those actually have an electron beam inside that is basically the same thing that this guy invented. Use magnets, take an electron beam that hits this paint that's on the back of the glass. The paint lights up when it gets hit by an electron beam. So yeah, then Dalton realized that since atoms are neutral, they have this, he came up with this idea called a plum pudding model, where it's like, here's an atom, there is positive paste with these negative particles in it. So like, Thomson figured out a way to rip those out, and due to chemistry and electrochemistry and the understanding that you could like energize things and extract electrons, they knew there were electrons in here, but they didn't realize how it worked. Then we come to the actual gold foil experiment was actually from 2 other guys. Can't remember their names. But Rutherford is the guy who used the gold foil experiment. So Rutherford who basically said there is this thing called a nucleus. Sorry? Yes, absolutely. Right? That particles pass through the foil in empty space, which kind of knocks this thing down, but then also that some of the particles bounced back. So it meant there was empty space and then just a few concentrated. To make sure you understand the magnitude of the size of a thing like that, if, I don't know if I've said this to you before, if I have a ping pong ball and the ping pong ball is a neutron, well, let's say it's a proton, sorry, ping pong ball is a proton, and this is the center of a hydrogen atom. So there's a ping pong ball that is a proton, and that's the center of a hydrogen atom. Where in our imaginary space, where is the outside of the hydrogen atom? The 1s sublevel. Yeah, it's like about a mile away. So what is a mile away from here? Like Garvey?
My house.
Yeah, right. I mean, that's past Broadway, isn't it? Is it Mission? It might be Broadway. Whatever. You get the idea. It's a lot, right? So, and that's a hydrogen atom, which is just a proton and then one electron in the lowest sublevel. So when you talk about bigger atoms, you're talking about 99.999% nothing, just space. Right? So just on a side note, how come her water bottle doesn't fall through her desk? If it's 99.999% nothing, why doesn't this fall through the desk? In fact, why doesn't your butt fall through your desk?
Electrons move around really fast.
Yeah, it's the electron sublevels and orbitals, right? Those probability regions, remember you learned that in chemistry? That it's not like there's a BB walking around, rolling around in the skin of a basketball or something. It's that there are these areas of statistical probability where the electrons, and it's not even that the electrons move around in there. It's that the electrons shift in energy form. And then they have the possibility, if you're going to detect them, it's going to be in this range, right? And so those electron levels interfere with each other because those electrons don't want to be in the same level. So when one atom comes next to another, they bump into each other. Those orbitals do that. So when you touch something, you can feel it because as you put your finger to that thing, the outer electron sublevels are bumping into each other and repelling. That's how you feel something. Right? I mean, those molecules deliver the force that your muscles are exerting through into the kinesthetic receptors in your neurological system, and you can detect motion, you can detect pressure. All right, anyways, then this guy comes, his name is Bohr. He discovers that there are energy levels specifically. So it's not just a nucleus and empty space, that it's a nucleus plus energy levels. And then we come to the quantum mechanical model. The quantum mechanical model. What is a quanta or a quantum? What is a quantity? Yeah. If you have a quantity of something, it's not just, I mean, do you see it's more than just a number, right? It's like a number that you have, right? Like, this is my quantity of something. So it's like a package of items, right? So the quantum mechanical model, what that means, it has to do with this concept that connects matter and energy, right? All of matter is sort of perceived in these two ways. Waves and particles. You know how, when we looked at light, what did we discover that light could do when you get the waves to kind of blend over each other? Yeah, remember, you could cancel out, you could have, so you could have destructive interference, you could have constructive interference, bright lines, remember this? Yeah, hopefully. So we know that light behaves like a wave. That's obvious. Okay. Do you remember what I also said about light? I think I said it here. That light, yes, light has momentum. Okay. And did I show that thing? No, I think I should. Oh, whatever. Light has momentum, which in order to have momentum, you have to be what? You have to have what? What is the formula for momentum? Mass times velocity. Light obviously has velocity, we just talked about that. But do you see what that's saying?
Light has mass.
Right? It's almost as if light has mass. So light has momentum, so it behaves like a particle. Light also has frequency, so it behaves like a wave. Right? And this is kind of the wave-particle duality of light theory that was actually very hotly contested, and I think like the 30s or 40s or something like that. Right? It was pretty popular. Yeah, because I think the quantum mechanical model that sort of blends these two together came in like the 50s or 60s. Yeah.
Just wondering, how does light obtain velocity?
Well, it's how it's released, right? How is electromagnetic radiation released? So where do you see light coming from?
Sun.
From the sun, from a light bulb, from something that's hot, right? So when you excite, when you give energy to particles, those particles basically jump up in energy levels in the atom. You know, there's different levels. And then they jump up levels, and when you stop giving them energy, it jumps back, it falls back down. When it falls back down, it releases energy. And that energy that gets released is a photon, and that's light. So that can happen through chemical stuff, it can happen in all different ways. Okay, questions about that? All right, let's see. Yeah, okay, that's cool. Okay, now the thing that actually really sort of brings these two together, that pretty phenomenally turns light and electricity and some other things together, is this thing called the photoelectric effect. Anybody here ever seen a solar cell? So no one here has seen a solar cell? Has anyone not seen a solar cell? What?
Is it those things on the solar power calculators?
Yeah.
Oh, yeah, yeah,
Right? Everybody's seen a solar cell, right?
yeah.
Wow. Okay, sorry. Photoelectric cell. Photovoltaic cell? Okay. All right, well, you've seen it. So, you know, it looks kind of
I've seen a
blue.
little plastic square.
Yeah. You know, it looks bluish, and it's kind of shiny, but not really. You know, like you look at it certain ways, it kind of looks reflective. Is everybody okay with what I'm saying here? Does it sound familiar? Grayish, bluish, whatever, yeah, something like that. So what that is, that's a single piece of silicon that has certain materials put in it. Because what, I think this guy, what was the guy's name? His name was Leonard. So the guy who came up with this, his name was Leonard. His last name was Leonard. That's like some guy like, oh, I'm Leonard. He discovered the photoelectric effect. What he discovered was that certain types of metal, when they're exposed to certain types of electromagnetic radiation, gain electricity. They gain an electric potential. So what he saw was, let's see how good this works. What he saw was that if you hit certain types of light, let's see. Nothing's happening. How do I do this? Oh, okay, cool. Can you see my little light here? And I put it on 100% intensity. See what's happening? What's happening is I'm hitting this thing right here with a certain frequency, 400 nanometers of purple light. Right? I can go over here. Ooh, man, this thing is, okay, it's not very receptive to 100. See how it's picking up?
Oh, it's kind of
Yeah, you can find a place. So this particular metal is pretty sensitive to that. What's that? Like in real life, when the electrons are released, then there's going to be like a random motion. So that one, what happened is something hit it or it bumped into one, and that took away its kinetic energy. So now it just flows through drift velocity through the rest. So different one. It's all random. But anyway, I gotta shut this off. All right. So what we have is a piece of metal here that when you hit it with light, it releases or emits an electron. That is the photoelectric effect. I mean, it makes sense, right? Photo, light, electricity, right? Photoelectric effect. It means light gets turned into electricity. And that's what solar cells are based on. Right? Solar cells, sadly, still are less than 20% efficient in converting light and converting solar energy into electricity, because they only operate in certain narrow bands. So if we do this, turn this back on, we can see here we have a current, right? And then we can go through here and we see our current drop. Up here, nothing, right? So what that means, what I'm trying to show you, is that each material, each metal, or each semi-metal, right, metalloid, silicon, whatever, is specifically situated to a certain frequency of light, right? That frequency of light has, so it's kind of like, think of it like the photons that are coming in, their size is a function of the frequency. The wavelength is a function of the frequency. So then the wavelength has to kind of fit the structure of the metal. So imagine that you could put on your special glasses and you could look at matter. If I look at matter and I could like, wow, zoom in and actually see the electron levels on the outside, what would they look like? You've seen drawings of this in chemistry. It's like, these kind of areas of probability, circles, these balloon-looking things, all kinds of weird bumps and contours. Does it make sense to you that a specific material might fit a certain wavelength better? Right? Do you get what I'm saying? So, like this metal has a bump like this size right here. So big photons come in, and they just bounce off. Little tiny ones go down in and bounce off. They might get a little bit of effect, but they bounce off. But if you get the right size, it just comes in, boom, and gets absorbed. That's what's happening here. These wavelengths are too big. They just bounce off. They don't absorb at all. But these wavelengths are so small, they fit in, but they just don't optimally fit in. So it's not perfect. Some of them will go in and bounce back out. But if we find that one perfect spot there, we can see that 196 nanometers is exactly what this particular material is set for. The structure of its outer orbitals allows that photon to come in, kick up an electron, right? And when actually it's even more than that, it comes in and gets absorbed. And when it gets absorbed, it kicks out an electron. And then the electrons go and we work. Okay? Now, here, if I take this and push it, flip the battery backwards, you see what I'll be able to do eventually?
Rather than reach to the side.
See what happens? Right? And they even showed you, see the little symbols
Oh,
here?
it's absorbing all of
Yeah, see what's happening. What I'm doing here is I put a voltage across this photoelectric cell, across this piece of metal semiconductor. And that voltage is the perfect amount to prevent these electrons from reaching the other side. Right? This is called the stopping voltage. Right? Or V sub-zero, and I'll talk about that in a little bit. But okay, so that's the photoelectric effect. Photoelectric effect is very significant. Obviously, solar cells are one. Has anybody here ever gotten an X-ray? Okay, do you know how Roentgen, I think it was Roentgen, first discovered the X-ray? Yeah, or the concept of the X-ray, right? He found some uranium ore. I can't remember what it's called. It's called some bauxite or something. No, that's not it. Yeah, whatever. He found some uranium ore, the ore that they used to extract uranium. And then he had it in his lab, and he was taking pictures. So he had undeveloped photographic paper in a box. And then he set the uranium ore on top of the box. And then it was unopened. And then he went to make some pictures. And when he made pictures, every one of the papers that was in that box had a big giant black splotch right in the middle. And he's like, wait a minute, this box was unopened. And what he realized was it was that rock. Something in that rock was emitting something that was penetrating the box and activating the photographic film or a photographic paper. And then that's from one thing led to another, and he figured out that's how, there's something in the rock that does that. So what he does is he sticks it in a little lead box, and then he holds his hand in front of the photographic paper, and then opens the front of the box, and then just lets whatever that magical crap that was in there is beaming out, hitting my hand, and then close the box, develop the film, and you can see through my skin, and you can see my bones, and you can also catch cancer, which is pretty much how most of those early pioneers in radiation and stuff, they died of cancer. Marie Curie, Becquerel, Roentgen, all of them.
The thing, when you take an X-ray, the thing they put on you,
Yeah.
like, what is that made out of? And how does that
Lead.
stop it? Oh, so that. So then, if they're taking an X-ray and you pull off last minute, like, is that automatically?
I mean, it's not like you're gonna have a mutated kid or you're not gonna die right away, but if you do that enough, then you'll get cancer. Yeah.
Wait, so what was in the rock?
The rock was decaying. The uranium, which I actually talk about in a minute too, and it was emitting alpha and beta particles. And I don't think it was emitting gamma radiation, but there's three types of radiation: alpha, beta, and gamma. And then the alpha and beta particles were passing out of that. The beta particles are the ones, and the gamma radiation is the one that goes through stuff. And then the alpha particles bounce off. And alpha particles are the things that make you get sick because they're radio. What's up, man? Okay, so if you've gotten an X-ray, then it is bad to give a bunch of people cancer, right? That results in lawsuits. So how can we do a process that gives us X-rays, which pass through material and allow us to see inside of stuff without having radioactive material lying around and nasty, dirty, like radioactive particles? True, maybe you could try to filter out some of that stuff, but the photoelectric effect is a really cool thing, because what did this do? It took what and converted it to what? It took light and converted it to, some form, like electrons, right? Photons, electrons. Well, what happens if you reverse the process? Then you get a specific type of photon, right? And it's not just light. It's like, well, duh, my flashlight can do that too. But it's a very, very, very high energy. So it's kind of like a light bulb, except you put in like 30,000 volts into this light bulb. And then it's so high energy that when the piece of metal gets excited, it doesn't release light, it releases X-rays. So when you look at that X-ray machine at your dentist's office or your doctor's office, you could touch it. Like you could put your head against it, right? You're not going to get cancer. Like you could hold onto it for a year and you won't get cancer. Yeah, that would look weird, but hey, but as long as you don't turn the machine on, there's no radiation. But when you turn it on, you hear it, right? It's like they say, all right, wait, then you hear, that is 30,000 to 60,000 volts of electricity at a good amperage, an amperage that will kill you, right? Passing through that piece of metal. And then because it's so high, boom, X-rays shoot out that thing, go through you, and then into the detector. All right, so X-ray machine is a big bonus, right? And that's something that's helped our society quite a bit. All right, okay. So if we take a look at your equation, your formula sheet, this is the first equation. Kmax equals HF minus phi. All right? Kmax, what does Kmax mean? Maximum kinetic energy, right? That's obvious. Now, everything else they tell us. H is something called, I thought H was Planck's constant. Oh, yeah. Ha. They did tell us. Right there. H is called Planck's constant. Okay, so it's right up here in your givens, right? And Planck's constant is a constant that allows us to see some things, right? Phi here is called the work function, and Kmax is the energy of the electrons as it comes off of this thing. So this is about the photoelectric effect, okay? And what this means, well actually let's take a look at the first equation up here. This means that energy in an electromagnetic wave is equal to Planck's constant times the frequency. So if you pick any electromagnetic wave, and then you can calculate the energy in that wave by multiplying by Planck's constant. Okay, so for example, anybody here have an AT&T cell phone? Because I know that one. No? Okay, never mind. T-Mobile, okay, I know T-Mobile. T-Mobile's 1700 megahertz, I think. So when you turn on your cell phone, it has a signal that uses 1700 megahertz as a frequency. Okay? So, take Planck's constant, I think 1700, what, who cares? Which is 6.63 times 10 to the minus 34 joule seconds, and multiply that by your frequency, 1700 megahertz, and see what happens. What do you get? Remember, 1700 megahertz is 1700 times 10 to the 6 hertz.
Why is there a UC?
What's that?
Is
Oh,
there-
that's if you multiply by the speed of light. That's like my mind. You'll see. Okay, what'd you get? I mean, this is basically 7 times 10 to the minus 34, and I told you I told you 1700, which is actually 1.7 gigahertz. So 1.7 times 7 is going to be like, what, like 11 or something. Yeah, so like say 12, and that's 12, 9 to the 20, 25, minus 25?
Yeah.
Is it something like that?
1 times 10 to the minus 24.
Oh, okay, 1.1 times 10 to the minus 24. So, how many joules of energy are passing into your head when your cell phone rings, or when you talk on your cell phone? 1.2, whatever, times 10, 1.1 times 10 to the minus 24 joules. This is a small number. Cell phones do not cause cancer by talking.
Those are ways of stupid when people start talking like this,
Yeah,
because they thought that only give them cancers.
it doesn't, yeah.
What about those radar
See
cell phones?
blackberries give you cancer.
No, I like blackberries, they taste good. I don't know. Maybe they have a higher power coming out of them, but still, even if you have a Bluetooth anything, right? Bluetooth operates at 2.4 gigahertz, which above your 1.7 is about a third higher. So, oh no, we're at 1.7, right? We're at 1.7 times 10 to the minus 24 joules of energy. So it's not very much, right? So yeah, have no fear there.
What about those radioactive cell phones in the 80s?
Oh, like the big one. I don't know how many watts those were. You know, the big StarTAC flick ones. Those are crazy. With the battery pack, that's like, I don't know. Yeah. I mean, my dad had a cell phone that you carried in a briefcase. So it was a briefcase, and then you set it down, open it up, and you pull it out. That's awesome. It's pretty funny. Okay, so if I give you a frequency for electromagnetic radiation, you should be able to calculate the energy. Okay, so please understand where I'm going with this. Because we just said this is the photoelectric effect equation. And the kinetic energy of the electrons is a function of the energy of the photon coming in. The photon coming in has frequency f. You multiply that by Planck's constant, and you will get the energy that photon brought. You have to subtract something called the work function. The work function is kind of like the energy that it takes to get you out of bed. Right? Like your day requires a certain amount of energy. But that certain amount of energy doesn't happen unless you overcome the work function. Right? It's, for some people, it's harder than others, right? But so first, so you kind of like have these electrons in the metal. Here comes a photon. Bam! The photon has E energy, a certain amount. So when it comes in, you realize, do you see what I'm saying? The first thing that has to happen is you have to kick that electron up. You have to get it awake. You have to get it out of bed. That's the work function. Now, whatever energy is left over, boom, that goes into the kinetic energy of the electron. Now the electron can go do some work. All right? That's the photoelectric effect, number one. Number two, we just calculated or got the equation that shows the momentum of light. Right? So if you could calculate the momentum of the photons that come off of your cell phone. And you could do it by saying HF is based on the frequency, divide HF by C, and you get the momentum of your, whatever, the electromagnetic photons coming off. Well, photons are usually associated with light. The electromagnetic waves coming off of your cell phone. Right, and we're all aware that radio waves, microwaves, infrared, optic light, ultraviolet, UV, X-rays, all that stuff. We know that that's all the same stuff. Yes, it's all like the only thing that's different is the frequency and the energy that it carries. All of those things are created the same way, by exciting charged particles. Because when you excite them, you move them. When they move, their magnetic field moves, they create a magnetic field, and their electric field moves. When you do those two things, you send off radiation. Okay? All right, so we've got those two. Now, so this first thing is just about energy. How much energy does light have? Boom, that's it. You see a question that asks you to do something with light and its energy. Bam, Planck's constant, frequency, done. If you see something that talks about the photoelectric effect, bam, there it is. Okay, and remember with electrical systems, right, you can calculate the amount of energy in a system because you know that in volts is what? What is the volt made up of? What are the two things? A volt is a what per what? Joule per coulomb. A volt is a joule per coulomb. Okay, so that's how you can bring this in. You can bring in volts on this side. All right. Okay, this is called the de Broglie wavelength equation. De Broglie figured out that everything is waves, including the chair you're sitting on. Everything is just quantized energy. It boils down to it, everything. Right? And it first happened because some people figured out that you could send electrons through a kind of prism. Oh, you could use an electron beam through diffraction. You know, we use light, right? And we send it through a single slit, through a double slit, and through a diffraction grating. And we got those patterns. Remember this? Yes, hopefully? Okay. You can do the same thing with electrons, actual matter. And what these people discovered is that when you did that, you created a diffraction pattern with matter, which is kind of astounding because you would expect that from waves. And then what de Broglie figured out is that just means that everything has a wavelength. So you can find it out, right? You can use Planck's constant, and then use your momentum. So if you want to find your wavelength, run down the hallway, we'll measure your velocity, take your mass, and then use de Broglie's wavelength, or de Broglie wavelength equation. So for example, how much you weigh?
160.
Okay, so let's say 50 kilograms. So let's say he's running at 5 meters per second. 50 kilograms, 5 meters per second, 250 kilograms meters per second. That's his momentum. If you take Planck's constant, which is 6.63 times 10 to the minus 34, 6.63 times 10 to the minus 34, divide that by 250. And then we can find Mr. Branch's wavelength. What is your wavelength?
2.65 times 10 to the minus 36.
Okay, so it's kind of small. So if you want to constructively interfere with him, you're going to have to find something that matches his wavelength. Now, how could you do that?
That's the one
Yes. See, we're all about the same scale. That's why we can interfere with each other's wavelengths. Right? Why can I screw up his momentum? Because my de Broglie wavelength is on the same order as his. You know what I'm saying here? Because if I had a much bigger wavelength and I tried to run at it, I'd just like pass right through. Do you get what I'm saying? So for example, if I had a much bigger wavelength, for example, radio waves have a wavelength of up to like 30, 40, 50 meters. That wavelength goes right through him.
So if you get someone that moves faster, I think you go through things.
If it has, it's a function of the size of the wavelength. So if the wavelengths are similar in magnitude, probably like 2 or 3 orders either way, they're going to bump together, right? Light doesn't go through you without causing severe problems, right? And light is in nanometers, so that's even nano. That's like 25 units away from your wavelength, and it still interferes. All right. Anyways, finally, the last thing is probably the one equation in modern physics that everyone knows. E equals mc squared. What this means, okay, this equation will pop up in a problem where you'll have a decay. You'll have something that breaks down. Remember that uranium that I talked about that was on that guy's desk? That uranium breaks down into other stuff. Polonium, palladium, plutonium, thorium. All these things come from that because that big fat atom, uranium, cracks into little pieces. When it cracks, it makes smaller pieces. But some of that crack is actually just released as energy. And you can calculate this. Yeah. Oh, maybe it did. That sucks.